Yeah, as you said, my name is Eike Cramer. I'm a student at the Eike 10 in Jülich, and today I would like to talk to you a bit about some of my recent work concerning generative modeling, and in particular about normalizing flows. Now, this work is joint work with Raul Tempone, whom all of you know, I suggest. I think, but it's also done with my supervisor, Alexander Mitzos, as well as my group leader, Manuel Dahm. Now, the work is particularly concerned with normalizing flows in the context of manifold density estimation. But for a start, I would like to give you a general introduction on what deep generative models are. And the basic idea behind deep generative models is to model somewhat difficult to describe distributions of data using neural networks. And this can be done a couple of different ways. Very popular approaches that allow strictly only for sampling are these generative models, meaning the generative adversarial network, also known as GAN, but also the variational autoencoder, VAE. Now, if you're interested in describing also a likelihood function, you might want to use one of the autoregressive methods. Those are the masked autoencoder, but also the masked autoregressive flow. Now, finally, the normalizing flows, which I want to talk about today, they kind of combine these two things. So they allow for both sampling as well as describing density distributions. Now, the general approach behind generative modeling usually is to describe our data distribution that we see here on the right. P of x is our likelihood function. We describe this as a neural network transformation of something simple that we know. For example, here, this Gaussian distribution. And really, in general, there's no limit on what the type of data we want to describe. So we can describe things like we see here, images, like the MNIST data set, which is very famous, but also images of faces. But we can also describe things that I'm more interested in, which is time series, and in particular here, these renewable energy time series. And we see here this example of photovoltaic power generation. Now, as I said, we want to talk about normalizing flows today. And if you dig a little deeper into the literature on normalizing flows, you will find two basic conceptions about them. And first one is that they are incredibly hard to train, meaning that they are really, really hard, prone to overfitting. And even if we get the validation and test loss to show good results, a trained normalizing flow is still prone to sampling outliers. So yeah, what this looks like, I can show you here with this example from time series. And you might want to say here at first sight, well, this looks good because this shows the general curve of a photovoltaic power generation behavior over one day. However, if you zoom a little closer, you'll find that the data is actually noisy and fluctuates around what you would expect to be actual data from solar power generation. And we see here that we even get this unphysical, physically impossible result of negative values that we really don't want to have in this type of data. Now, at first sight, you might say, well, this is just a little bit of noise, and this might just be a poor fit. But I do want to show you today that there's actually more going on, and there's a fundamental issue with normalizing flows. And to kind of show you where this is based, we have to change our perspective a little bit here on this data. And to do this, I'm going to switch it now from the time domain view of this time series to a state space description, as we see here on the right. So we're actually looking at these 3 hours that I've highlighted: noon, 1 p.m. and 2 p.m. And when we look at this data in this domain, we see that the data doesn't actually occupy the entire space where it resides in. Much rather, it's embedded in a lower dimensional subspace or a manifold, if you will. Now, I want to show you today that manifolds violate necessary conditions for normalizing flows. And we're also going to see an approach using dimensionality reduction through principal component analysis, such that we can still perform density estimation using normalizing flows, although we have data manifolds. Now, before we can start discussing what the effects of manifolds are, we have to understand how normalizing flows work in principle. And the fundamental idea of normalizing flows is to take the coordinate system of our data set and perform a change of variables on this coordinate system such that after this transformation, the data resides in a space but follows a Gaussian distribution. And if we find this transformation function f here, we can use this to describe the density of our data as the density in the Gaussian space. We see here PZ is a Gaussian likelihood function, and this Jacobian determinant factor, which scales the distribution to ensure that the volume of the distribution stays one, or excuse me, the integral over it stays one. Very importantly, we have to ensure a couple of things for this to be functional. And the first thing is that this transformation f must be a diffeomorphism, meaning it has to be a bijective transformation with both the forward and the inverse transformation are differentiable. Now, for this to be possible, we have to set up our lower dimensional or Gaussian space to have the same dimension as a data space X. So we can transform between spaces of equal dimensionality. Since for most data sets, we can't really set up a function that does this change of variables, we want to find something that we can train and fit to this transformation. We can do this using log likelihood maximization. And a function that is very widely applied for this change of variables here is the so-called affine coupling layer, and it's applied in form of the real non-volume preserving transformation, meaning we're setting up this invertible neural network structure just simply to perform this this change of variables transformation. The idea behind this affine coupling layer here is to actually split up the data vector into two halves, and then perform an affine transformation on one half of this data vector. And we see that here with Z2 on the right. And this affine transformation, both the scale and the shift values, they are outputs of deep neural networks. And there's really, and this is S and T here, and there's no limit on what these are. We can simply put whatever trainable function there. Now, the clue here is that the other half, the one stays untouched. It doesn't get transformed. If we want to build the inverse, the inputs, we only have to invert the affine transformation, and the inputs to the deep neural networks stay the same. Now, if we then flip this affine coupling layer upside down, we transform the remaining half of our data vector and thus have a full transformation of the data vector. And also, again, there's no limit on how many affine coupling layers we want to use. So I've put 2 here, but it could be 3, 4, 15, however many you want. We just have to consider that the complexity really goes up a lot by adding some of these layers. Now, this format of, or the structure of invertible neural network has some really nice advantages. Mainly, it is easily invertible. As I said, we can simply, we only have to invert the affine transformation, which is trivial. but also it has an easily tractable Jacobian determinant, simply because the Jacobian of this transformation is a lower triangular matrix. Now, to summarize this a bit, is that real MVP here builds a diffeomorphic transformation where we can be sure that the transformation is a diffeomorphism. And what this does is we get a unique transformation between points in the two different spaces. And this is really important when we now go on to discussing manifolds. Because here, when we bring back this figure that or this GIF that I've shown you in the beginning, we see now that because we have this lower dimensional embedding of our data, we really have a lower dimensional object. Now, we're now trying to match this exactly using a diffeomorphism to a Gaussian distribution. Well, what we then end up trying to do is matching what here is a plane with a three-dimensional object, the Gaussian distribution. In 3 dimensions, this is a ball, but in higher dimensions, yeah, even something else now. Yeah, like I said, this is going to be problematic because we're trying to match spaces of different dimensionality. And just to underline what is going on here and maybe visualize in a different way, I want to show you this vector representation right here, where we have on the left side the Gaussian vector and on the right side the data vector, only that in reality, the Gaussian vector is an independent multivariate distribution where the data vector is not. It's a non-independent, and we kind of have this fake dimensions that don't really where no data is present. So what we see here is that diffeomorphisms are really not the right idea to build this match between a data manifold and a full space Gaussian. And what happens is, if we now fit a data manifold and try to match it to a Gaussian distribution, there's a lot of space in this Gaussian distribution that just simply doesn't get matched to the data space. And in return, if we then sample from this Gaussian and use the normalizing flow to sample, we automatically and by design end up sampling data that is not part of the data manifold, meaning we're destined to be sampling outliers. And this is also something that I've shown you in the beginning with the noisy data. Now, the question is, what do we do? And at this point is where the dimensionality reduction comes in. Now, the idea behind using dimensionality reduction here is because we have this lower dimensional space, a lower dimensional embedding of the data, we can reduce its dimensionality, cut away the parts that have a 0 probability, and then perform the normalizing flow, the change of variables here in a lower dimensional space where that is not influenced by the data manifold. Now, if we want to do this, we have to consider that this dimensionality reduction is still a transformation. So we do have to consider it in a change of variables. And because the dimensionality reduction has a non-square Jacobian, we have to use this generalized form of the change of variables formula. Now, obviously, it would be nice if we had an exact map phi here that reduces the dimensionality and reproduces the data without any loss. But for most data sets, we simply don't have that. So what I would like to propose here is to use the principal component analysis. And on the next slide, I will show you that this actually has some very nice advantages to it. Now, principal component analysis in general is a linear dimensionality reduction technique. And yeah, the basic idea is to assign a new coordinate system, a new orthogonal coordinate system to our data, where now the axes of this coordinate system point into the directions of maximum variance. We then omit the axes that point in the direction of lowest variance or no variance at all. We end up with this lower dimensional representation of our data that still is able to describe most of the information in terms of variance that we have. If we now bring back this generalized form of the change of variables formula, we see we still need the Jacobian of the dimensionality reduction. However, because the PCA is linear, we can see that this Jacobian is always going to be this matrix V here. Now V is the matrix of right singular vectors that comes from the singular value decomposition. And this is by design of the singular value decomposition always an orthonormal matrix, meaning the truncated version is a semi-orthogonal matrix, which makes this determinant expression here always equal to 1, independent of the data set that we're using, just simply by design of the PCA. So this does a couple nice things for us. And first thing is that we don't need to consider this in the change of variables, meaning during training, we don't have to solve this expression, which is potentially going to save us a bunch of time. And much rather, we can move the PCA from the training the normalizing flow simply to pre-processing, which is also nice if you look at things from a coding perspective. Now, I do want to show you some computational results. And for that, we're going to look at scenario generation here. And the idea about scenario generation in the way that we apply it here today is to learn the distribution of daily intervals of these time series. So we're not looking at the time series as we see it on the right, but rather we cut it into pieces and then look at the distribution of the individual days. And then each day is a data point in the distribution that we want to learn. Now, we're going to train a couple of different normalizing flow models here. The first one is going to be the full space normalizing flow, where we're going to use the real MVP model that I've shown you in the beginning. And we're also going to train the principal component flow, where we use the real MVP model in the lower dimensional space. And this PCFX here, the X is going to know the number of principal components that we're considering here in the PCF. Now we're going to look at 3 different time series today, 2 from renewable power generation, meaning solar and wind, and also a demand time series. All 3 of these time series are sampled in 15-minute intervals. So the data points that we're looking at actually have 96 dimensions, so have 96 steps per day. Now, really importantly, we have to look if we match the correct distribution. I mean, we can't look at the 96 dimensional distributions because we simply don't have 96 dimensions. So what I want to show you instead is the distribution of all data points. And here for the photovoltaic power generation time series, we see at first sight that all 3 networks here actually give quite a good match of the PDF. However, if you look a little bit closer, we will find that the full space normalizing flow actually gives a little bit of a compressed version of the PDF, meaning that there's more data where the density is already high and less data in the tail of this distribution. And while this isn't as obvious here for the solar data, it's much more obvious for the wind, where we have this high peak and this shorter tail over here. Now, in both cases, we see significantly improved results because of the dimensionality reduction. Now, the distribution obviously is not the only thing about time series, so we also have to look at the fluctuational behavior. And to do this, I would like to show you the power spectral density here. And just to avoid confusion, power does not refer to the unit of our time series, but only the power of the signal here. So it's actually the power of the amplitudes here in the frequency domain. Now here we see that for longer periods, and we see that all 3 networks actually match the behavior really well. And this is somewhat in line with what we saw in the very beginning, where at first glance, the data looked really good. However, if we then look at shorter periods, we see that the full space normalizing flow has higher fluctuations than our target distribution. And we actually have this additional noise fluctuations that we didn't see in the historical data set. Now, if we now reduce the dimensionality, I see that we get this very good match of the fluctuation. And if we reduce the dimensionality even further, we actually see this filter effect where we have filtered some of the noise that we saw in the data. Now, this filter effect is not as obvious for the wind data. However, we again see a mismatch of the fluctuational behavior with the full space normalizing flow. And again, we see a much improved version here with it after dimensionality reduction. Now, this consistently lower fluctuational behavior, we kind of attribute this to the distribution being compressed around the peak, meaning the amplitudes are simply lower. So here the PSD also is lower. Now, what I've shown you so far makes the PCA dimensionality reduction look really, really good. And I don't want to say that it isn't, but we also have to consider cases where it doesn't perform perfectly. And one of those cases is the load demand. Now here, looking at the probability density, we again see for the full space normalizing flow that again, it struggles to match the distribution well, and we again see a somewhat improved fit through dimensionality reduction. If we then go on and look at the power spectral density, we see something else. What we see here is that despite of dimensionality reduction, we get significantly more noise in the data that we didn't see in the historical data set. Now, the question, what has happened here is, now the PCA is unable to fit this manifold exactly. So we probably have somewhat of a nonlinear manifold here. And what happens is that simply by reducing the dimensionality through PCA, we get this other fluctuational behavior, this mismatch right here. And you can see that here because I've added this blue line, which is denoted PCA 10, which is simply what I've written up there. So we reduce the dimensionality using PCA, rebuild the data. There's no normalizing flow involved. However, if we then compare this to the normalizing, the PCF data, those look very similar. So the normalizing flow actually succeeded, but the PCA did not. Now, what we take away from this slide is not that PCA per se is bad, but we have to check if it applies to the data that we're looking at right now. Now, concluding, what I've told you today is that if we have data manifolds, then standard normalizing flows are by design unfit to be trained on this type of data. What I've also shown you is that dimensionality reduction can help with these issues, and in particular, the PCA has some really nice advantages when working with data manifolds. Now, obviously, the next step from here on out would be to go for a nonlinear dimensionality reduction approach. However, for today, I would simply like to give a shout out to my graduate school, the HCC, and yeah, thanks all of you for the attention. Thanks all for the invitation. And yeah, should you have any questions, please go ahead. I'm happy to answer.